because you have the YouTube videos that you can watch to review. So just some things that I didn't really talk about as explicitly as I wanted to last time. And the first is the importance of units. And everybody knows how important units are. And so I'm just going to go through a few concepts, and then I'm going to do some things that I think are quite a bit more interesting. But remember, this is about the simplest rate equation or kinetic equation that you can write down. And so you look at this and you think about this, and you know that this is a unimolecular transformation, right? And so if you go ahead and you write down the rate law for that, which we did last time, you can talk about the loss of a reactant and the derivative of the concentration of A. And as I said, I tend to get lazy and not always remember my concentration symbols. But the loss of the concentration of A is equal to the rate of the formation of the concentration of B with time. And we can say, and I haven't been able to figure out completely how to make this blinking go away. I don't know if I'm going to be able to, but it's not there in the YouTube replays, which is good. And so if we write that down, that's simply equal to what? K times what? You guys remember? Times the concentration of A, right? All right. So if when you think about units on this, units for rates are always in what kind of units? Molar per second, right? So you can see the upper part. You don't have to use molar. If it's more convenient, you could use micromolar, but some kind of concentration per second. So sort of like like miles per hour or something like that as a rate of driving your car. And of course that's true for that and true for this. So if you look at that, what can you say the units on the rate constant will be?
Per unit time?
Yeah, good, Kyle. And you knew that because you know that that's molar. And so if you need to figure that out, you can say, therefore this must be reciprocal time. So that rate constant is per second. If you work on ribozymes, you might use per minute or per hour, so the numbers don't sound so small. So if your rate is 0.001 per second, you might turn that into something bigger per minute, or it'd even be like, per hour would be fast. So, okay. So that's just a little bit about units. And so if we take that and pop that up in the corner there, we can look at another reaction, which is not unimolecular, but let's say bimolecular. A plus B goes to C. So this is bimolecular. And overall, this whole concept of unimolecular, bimolecular, that's called, as you all know, just to work on your vocabulary, the molecularity of the reaction. So what would come next after bimolecular? Unimolecular, bimolecular, trimolecular. What's the likelihood of trimolecular really happening?
Not very likely.
Not very likely, because things have to collide to react. And so 2-body collisions are likely, 3-body are unlikely. So it's pretty rare, and often when you write it down, it's really because it's made up of some steps that are bimolecular. So I'm just going to stop here, but we can write down the rate for this, right? It's just minus dA dt, the loss of that reactant here, or that's equal to the loss of B, and that's equal to the formation of C with time, and that if this is K, let's call this, go back up here, K1, K1, K2, K2, then it's K2 times A times B. And what's the units on rate for a bimolecular reaction? We know for a unimolecular reaction it's molar per second. How about for a bimolecular reaction?
Second and molar. 1 over second
I
molar. 1
can,
over second and molar.
1 over
Second and molar.
second molar squared?
Yeah.
No.
Just
Not for, no, just for the rate.
That's
If
not
you,
what she said. She said 1 over second molar. Like second and molar.
oh, inverse
all
molar,
over.
inverse second.
Yeah.
Yeah. But I'm asking what are the units for rate, not the rate constant. So are rates and rate constants the same thing? No way. Okay? You can see that up here. This is the rate, okay? A rate is molar per second, and a rate constant, they definitely have different units. So if they have different units, we know they're not the same thing. Okay, so what's the units on the rate here, Kyle?
This would be molar per second.
Still molar per second, right? Because it's always molar per second, and you can see that just by looking at the equation. It's molar per second. And so we know that this is molar, and we know this is molar. So then this is inverse molar, inverse second. Just by using, that's what you said?
Thank you.
I'm sorry, I couldn't understand. That's what that rate constant is. So rates are always the same. Always have those units, and the rate constant depends on the molecularity. And maybe this is coming because I'm hitting the edge of this. No, not necessarily. Okay. All right, so let's move on, and just a couple other things that I wanted to review, and one is the notion of saturation. Okay, so we talk about this a lot in enzymology, and so when you guys think of saturation. For me, there's a couple things that come to mind. So last time, what if I do it like this? It doesn't make any difference. We wrote down a mechanism that looked like that. And so when you think of saturation, what comes to mind in that terms of that mechanism? Anything? So sometimes we'll write an enzyme like that, Pac-Man. Do you guys know what a Pac-Man is? Or am I like out totally dating myself? I used to play Pac-Man when I was a kid. So that's the Pac-Man, that's the E. And then S, we'll write like that sometimes. And then when they bind, it'll look like that. And that enzyme can't pack another substrate in there, right? So it's called we consider that to be saturated with substrate. All right. So so that's one picture of saturation. Often, although not always, but often, and we talked about this last time, is multiple turnover. And in multiple turnover, we said the enzyme's present in limiting amounts, or the initial amount. And so the enzyme can be in this case, two different states, right? Free or bound. And so if it's saturated, what is the enzyme? Is it free or bound? It's all bound. Okay. And so so if we do a plot of rate, okay, or initial velocity versus the concentration of substrate, at first what's going to happen to the rate? Well, if we have no substrate, it's 0, right? And then what's going to happen as we increase the substrate, Erica?
It's going to go up.
It's going to go faster. Is it going to go faster forever?
No.
No. Because this is what's going to happen, right?
Mm-hmm.
And all the enzyme is saturated with substrate. We can't go any faster. So it's going to do that eventually, right? And so that's the saturation point out here. And so then,
with the diagram you have, are you just, like, is that just representative of all enzyme? Like, are you saying all enzyme is bound to substrate so it's saturated, or that specific enzyme?
yeah. So let's
Call
like
that
let's like
saturation.
take a little like picture of what's happening at different points. Okay, and let's pretend, because I don't have a lot of room here to play with. Let's pretend that there's 3 enzymes. Okay. And so in this region, like one of them might be bound with substrate, but the other ones aren't. And then up here, if this is, say, 1/3 the rate, they're all 3 of them. So and then there's lots of free substrate around, right? And then out here, it would look the same, but with even more free substrate. So it doesn't go any faster because all the E is bound. Okay. All right. So with that in mind, we can do some different math. And so one of the things that I think that's the way I like to think about enzymes is in terms of the fraction of the enzyme that's saturated. And so mathematically, it's really helpful to write this down in terms of this concept. Fraction of ES, okay? And that's equal to ES over all forms of E. And here that's really easy because there's only 2 ways, as we said, that the enzyme can be. It can either be free or bound. And when the rate is maximal, what is FES equal to? 1. So it's always less than or equal to 1. You can see that in the math, right? Okay, it can never, the numerator consists of the numerator plus something else that's positive, and so it can never be greater than 1, but it can certainly be less than 1. All right, so let's take that and see what useful things we can do with that with more complex things. Okay. So last time we took this mechanism and we derived the Michaelis-Menten equation, and we derive this, that the initial velocity is equal to Vmax times S naught over Km plus S naught. And we used the steady state assumption to do that. And the steady state assumption was simply that the change in the concentration of the intermediate with time was 0. And so we wrote down the rate law for that, and we set it equal to 0, and then we solved it, and that's in the notes. And this was K1, this was K minus 1, and this was K2. And that's perfectly fine. And that's the way most people do it, and that's the way you'll find it in your textbooks. But it's not very general, and it's not as powerful as some of the other ways to do it. So I'm going to show you another way to do it now. And I think we need a new chalkboard to do that. Any questions? Okay. So another way to do this, let me put the mechanism back up here just so it's on this page. Actually, I think what I can do is grab it. Yeah, it's easier to write it over. It's small. All right. And the rate constants, as I like to do them. Remember, they're little k's, and 1 and minus 1 for the first step, 2 for an irreversible last step. And we're going to get more sophisticated here shortly. We're going to put EP in. We'll make things all reversible, and then we'll see how to handle it. But so we can write down a few things, and the first thing we can do is what we always do is we write down the rate and the rate here is equal to dp dt. Okay, because that's what we're interested. That's really just a definition. We know the units on that are molar per second, and we can write down, last time we wrote down the rate law for that. We know that that's equal to, and we're going to use the same thing here. It's just this step right there, right? And so that step is equal to K2 times ES, because it's a unimolecular process, and that's still true. Now, but what we can do is we can use the equation that, I'm going back to the previous page. It's up here. And what we can do is we can use this definition to redefine ES as ES is equal to the fraction ES times E total. You guys see that, right? Okay. So in other words, if I rearrange this, ES is equal to the fraction ES times E naught, where this is E total. The denominator there is E total. All right. So I'm going to go ahead and take this equation and use it. And you'll hopefully see in a second why that's powerful. So then this is equal to K2. And now in place of ES, I'll just write it's the fraction ES times total E. Like that. And let's just show that we can rederive the Michaelis-Menten equation if we use this approach. And so let's write down the equation for FES is ES over E plus ES. And now what I'd like to do is get this in terms of I'd like to get this in terms of KM. Let me just fix something here. So we're still going to write down and use the equation that we did last time, and that is that E times S over ES is equal to the Km. That's from our last set of notes. And so how can I connect these two equations, guys? What kind of algebra can I do to connect those? Like, we all know that KMs and KDs have all multiplications, and so we're throwing you like a curveball by changing the math and putting plus signs in. Anybody see the trick?
So if you want to get rid of one of the variables,
Yeah.
what can
Well, actually what I want to do is get rid of E and ES, and I want it in terms of S and KM, because we know the way that we play the game here is back here. We're going to have it in terms of S and KM. See that right there?
Mm-hmm.
Okay. And so I want to get this right, so I can rearrange this. You're on the right track, Erica, by dividing through by S. And now what I want to do is get E and ES out of there. Yeah, Laura?
Divide the fraction of ES by ES.
Multiply this by 1 over ES. Can I do that?
Or ES over ES.
Yeah, I can. I can multiply by the number 1. So if I do that, then I will be able to get rid of stuff by doing that. Now, there's Eric, you can grab that stool if you want there too. Alternatively, I could divide through by E, same idea, okay, rather than ES. And that's what I'm going to do this time, but the next time I will. It doesn't really matter. And that's basically a reference state, okay? And so, but you guys can see what's going to happen when we do that. We're going to end up with ratios, and then we can substitute in. Everybody see the trick? It's really important. If you really want to understand this stuff, if you really want to internalize it and make it your own and be able to do creative things with it, you need to see what the tricks are and when they're happening. Yeah, Jamie?
So in general, I know last time we talked about trying to get in terms of E initial and initial substrate. So is that in general what you're trying to do? Like you're just trying to get rid of intermediates and everything, just get substrate and enzyme?
Yeah,
Initial?
so yeah, because we know S not.
Right. So just
Hopefully
get rid
we
of
know it because we set up the experiment, we added it, and S is in huge excess, so free S is equal to total S, and so and we're interested in the Km, but we generally don't know E and we don't know ES, so we want to get them the heck out of there and get these other guys in there, okay, and so now it's just math, okay. Let me clean up the chalkboard. If I can, get rid of most of it, and you guys can probably see what's going to happen, but let's do it. And notice also the way that I'm writing these ratios and writing ratios inside of ratios. I'm writing them using like here. I'm writing them with a diagonal slash rather than a horizontal one. You can get more stuff on your equation without running out of space. So it's a convenient thing to do. So I'll do that. Okay. So once you do that, now you just have to substitute, and you can see what's going to happen. And hopefully, without even watching me, you can work ahead on your notes and be able to write all this out. But ES over E is equal to S over Km, and it's almost always the case that if you have ES over E, you have S over Km. The S's follow each other. And then you can just multiply through by. You can leave it like that. And I like to leave them like that from time to time. But you can also multiply through by Km. And now this can be substituted up into there to get, hopefully, let me just change one thing. To get that, and that's back to, and then this is Vmax. And notice how I'm choosing to just separate out the algebra. And I have, it's Vm times S over Km plus S, but we know that that last term is simply equal to the fraction of ES. And so it's Vmax times the fraction of ES. It's just kind of cool, right? And powerful. So we get the same answer. There's no steady state assumption that we did here. We did more of a fraction type of approach, which is much more akin to something that's called a partition function, which you guys might be familiar with. And the denominator in this here is called a partition function, and it's particularly obvious. Oops, why do we do that? It's particularly obvious here. Okay, and that part is Q or your partition function. Hopefully everybody's heard of partition functions. And it's just a statistical weight for each of the species. And if that sounds obscure, it's really not, because you can see the parallel between these terms and these terms. Okay, so the 1 goes with the E, and the ES goes with the S over KM. All right? And there's a summation, so we sum over all the species in solution. So why do we want to do that? Well, because most of the scenarios that we're going to encounter are going to be more complex than the one that we just looked at. And so last time, Eric asked me a question about what happens if it gets more complicated. Than this. And as we know, our research is almost always more complicated than the textbooks. So there's the one that we've been looking at all along. But let's imagine that there's a second binding site for substrate, and it binds to free enzyme. And to just designate that it's binding to a different site than the one in the upper bank, we'll have it bind to the left side. And I sort of hinted that we might talk about this last time, so we'll go ahead and talk about that. And that association has some binding constant that's associated with it, and we'll use KDs because we saw the power of KDs. They have units of molar, so we're always going to use dissociation constants. And I'll just have this be whatever the affinity is between E and S, to put S on the left side of the binding equilibrium like that. And we'll call that Ks prime. And so, if this is K2, then I can write down that the rate is equal to, well, let's go back. Right here, the rate was equal to K2 times the fraction of ES times E naught. And that's still totally true, because the rate is coming out of this part, right? It's for forming product, and all this other stuff that's going on is away from that step. Okay, so dp dt is still equal to K2 times ES, which means it's still going to be equal to the same that same expression that we derived on the last page. So K2 is still the same, E naught still the same, but that thing has changed, fraction ES, all right? And so let's go ahead and derive that, an expression for that. So fraction ES is going to equal to ES over the sum of all E. And how many E species do I have now? 3. That's right. And I can write them down. I'm going to write them down as E plus ES plus SE. And that's going to turn into my partition function. My partition function is now going to have 3 terms because I have 3 states that the enzyme can be in. And so once again, I'm going to need to pick a reference state, and we're going to use the same trick as we used last time in order to get this into a ratio of ratios. And I'm going to end up with ES over E divided by 1 plus ES over E plus SE for E. And it's always the case that what the term in the numerator is one of the terms in the denominator. The term in the numerator is one of the terms in the denominator. Okay, it's one of the species in the partition function. All right. So let's keep going. And now we can write this down in terms of S and KDs. Oops. And so ES over E is equal to KM. Sorry, S over KM. And that just came from what we had on the last one. And SE over E, this guy, can come out of that. And we can see that SE over E is going to be equal to S over KS prime. All right, so I'll keep on the same sheet. Then we can just go in and write down that the initial rate will equal K2 times E naught. Oops, let me fix that. Times the fraction of ES, and so let's go ahead and write that down. And if you want to, remember back here what we did is on this guy we multiplied through, this one right here, we multiplied through by Km. Okay, we can do the same thing here. And so we'll end up with now that, before I write the last term, that looks like the standard equation, Michaelis-Menten, but now when I multiply through, I get plus S times Km over Ks prime. And that's the final expression that I have. I'm just going to do, and I think I can still get all this in here, a few plots on this. So after I derive something like this, and I actually didn't look this up anywhere, so if there's something wrong with it, let me know. I just made it up. But I look at this, and I feel comfortable, at least to some extent, because the units are okay. All right, so I'm a big units person, and if you look at this expression, just to talk about units for a second, the units in the denominator on the first term, Km has units of molar, S is molar, and then in the third term, S is molar, and Km and Ks have the same units. So they're all molar. It means you can add them together. Remember, you can only add things together if they have the same units. So from a unit point of view, we have molar plus molar times molar over molar. So we can add them all together. And then in the numerator, we have K2 has units of Kyle, inverse time, unimolecular, and then the rate constant, then E is molar and S is molar. And you can see that that's going to come out in terms of a rate, molar per second, right? So it doesn't mean that my expression's right, but if it didn't come out with the right units, it would definitely mean it's wrong. All right, so when you're trying to do research and you're trying to create new knowledge and you don't have the answers, you need these gut checks all the time, okay? And so so it's really useful to do that. Now, if I was reviewing a paper, or right now I'm reviewing grants, if I was reviewing a grant and I saw an expression and it had, I'll just put something in and then I'll erase it, and it had a square. Won't let me write. There we go. It had a square there. I would know it's wrong. It has to be wrong. Or if for example you're reviewing a paper or you're looking at your own math and you see there's an s squared there in that term, you immediately know it's wrong because you can't add things together if they don't have the same units. All right. So it's really handy for spotting mistakes.
Before you move on with this,
Yeah.
can I make a comment?
Yeah, absolutely.
For the students that took Chem 540, I assume Ed O'Brien taught partition function treatment of thermodynamics. So anyone who took Chem 540, that final term with the ratio of Km to Ks prime, you should be able to go back and see the direct analogy there to the functional form for mathematics involving linkage to a conformational change or to a change in the assembly state of the macromolecule. The underlying principles are exactly the same.
Mm-hmm.
So that's another way that you could cross-check if you are well-versed in those kinds of expressions in the next class.
All right, so let's just do a couple simulations of what might be going on. So I'm going to grab, I need to go onto a new chalkboard here, and I just put the expression here. Okay, and so let's pretend, let's do two scenarios. So one, let's let Ks prime be about 10 times Kd. And then let's do a second case where Ks prime is about 1/10 Kd. So in other words, here it's weak because it's big. Big is weak. It's dissociation. And here it's strong. No math. What do you guys expect to see? Go back to the picture. This is Ks prime right there. If Ks prime is really weak, do you expect it to have much effect? No. Okay, so this is the other gut check to do these sorts of simulations and see if that works out. So let's just substitute in. And then I'll take the second term and put it first, and then Km over. I'm sorry, I made a slight error here, guys. This should be not Kd but Km. And so Km over Ks is
Phil,
what did I do wrong? I did something wrong. Yeah.
every time you write S, do you leave S not?
Yeah.
Because we're assuming it's
Yeah. Yeah. So Km over Ks. Oh no, this is right. Yeah. So Km over Ks is about 0.1 in this case. So it's Km plus S over 10. Or in other words, K2 times E naught over 1.1 S plus the Km. Times S. And so, and this part is Vmax, So the fastest this can go V naught is equal to V max. When S is much bigger than Km, it'll be S over 1.1 S, or V max over 1.1. So that's the maximal. So there's very little effect.
Isn't it 10 km? Dominator.
Here?
11s and plus 10 km, isn't it?
No, this is still Km. This is that term right there. Sorry, I moved them a little bit. Here's the S and there's the Km. And then this term here becomes S over 10.
But for like, you have like 10 and like when you're like multiplying 10s and you have to multiply 10k as well.
I'm just adding 0.1 S and S to give 1.1 S.
Okay. Gotcha. I thought it was 11.
Yeah, there's other ways to skin a cat, but yeah.
Okay.
Yeah, but then if I go over here and do the same thing, I get V naught is equal to K2 E naught S over S plus Km plus 10S, or that V naught max is now equal to V max over 11. So in other words, the rate takes a huge hit here. And so if you go ahead and you plot these guys out, and this is V max, this one goes just a little bit below, but this case goes way below, like that.
Sorry, Bill.
Yeah.
I can't read what it says next to sorry, K2 E naught S over S plus Km plus.
Oh, sorry, that's
20.
10S.
Oh, 10S. Okay.
Sorry about that.
Thank you.
Yeah. So you can see what happens is that Km isn't changed at all, but what happens is that it changes how fast it can go. And does that make sense? And if we go back one slide, it sort of does, because when you look at what's happening is that this S binding over on this side is just tugging on the equilibrium. And so if it tugs a little bit, then it has a little effect, but if it tugs a lot, then it has a big effect. And even if you add more S, it doesn't matter, because at saturation, it's going to pull toward SE more than it's going to pull toward ES. And so that also gives me an understanding of what's going on, and also gives me faith in the equation that I derived, is how I look at it. So then after I did this, I started to wonder, well, is there a way where that's a type of substrate inhibition, but you could imagine something else. And so there's different ways to think about things. One is, in the way we often, whoops. Okay. And the way that we often we do things in my lab, at least, is we go in and we have some idea, we do an experiment, it comes out different than what we thought it was going to come out with. And instead, what might happen is the data would look not like that, but you go in the lab and you get results, and it looks like this instead. And there's no way that this mechanism here can come up with that type of result. So it's good to kind of know what tricks the math can play or can never play. So this math can't do that. It can do this. It can depress Vmax down, but it can't bring it all the way back down. Okay, and but your data says that. So then you need to come up with. You go back to the drawing board. This is a drawing board. Literally, you pull out the drawing board, and you say, well, all right. This didn't do it. But we know it's coming from S. Where else could S bind besides to free E? To ES. And without doing any math, do you feel like that might lead to that result? Sure, it might. Because it could take, when S is high, you could go to completely SES. They're not competing with each other. Okay? So this is non-competitive, as I've drawn it, whereas the other one sort of was. Maybe in the other scenario, they have overlapping binding sites. That in this scenario, they might have overlapping binding sites. So they're mutually exclusive. I think about ribozymes, and so there might be two oligos that share a binding site. But in this scenario, they might not overlap at all. One might bind to one part of the enzyme and the other one to the other part. Okay? It's also possible that you could have everything going on at once. All right? So let's start out not with everything going on at once, but let's just start out with that. And you guys can now handle this. And you know how to derive this, so I'll do it rather quickly. And the main thing that we need to do is we need to calculate the fraction of ES again. Remember, that was the trick on these previous guys, including if I go back to here. That was what we did in that guy right there. All right? We calculate the fraction of ES. So let's go ahead and do that. In other words, this is the one that can, this is the species that can do the reaction. This is the one we care about. So we just simply write down the expression for that. We have three terms in our denominator in our partition function. And so now we need to pick a reference state, and I've been picking free E as my reference state. I could do that here, that would be perfectly fine, but I like to pick a reference state that connects everything, and we see that E doesn't connect directly to SES, but ES does. And so I'm going to choose that as my reference state. And like I said earlier when Laura suggested ES, there's nothing wrong with doing that. And here, there would be nothing wrong with doing E either. It would just be a little bit more math. And so when I do this, I end up with 1 over hopefully if I did my math right, that's what I end up with. And then I can reduce this guy down to 1 over, this is now, Km over S plus 1 plus, now I need some way to relate SES and ES, and so one can always write down equilibrium constants for any step that you want to isolate. So so you can have a Ks double prime. And here we'll just focus. Hi everyone. So this picks up where we got cut off at the end of the lecture. And you can see the rest of the math should be on the board here. You can see the three terms that are down below here that make up the partition function. And one of the things that we saw that makes this particularly interesting is that when we rearrange, is this third term in the denominator has an s squared. And so we can see that when the concentration of s gets very high, that term will dominate in the denominator, and that will cause the velocity to go to 0. In other words, in the limit of high concentration of s, the v will tend toward k2 e naught s over s squared over ks double prime, which will go to 0. And that is consistent with what we see here. And then I left you with just a few pointers, take home in terms of problem solving. First is to try to use common sense and chemical intuition, both in terms of writing down mechanisms and in terms of plotting them out and understanding how they behave, and also whether things make sense in the sense of the units and sense of the in the sense of the plots, and that sometimes we need to work backwards. So we derive equations that correspond to a certain mechanism that we've written down, and it has one behavior. We do the experiment, we have a different one. And so from what we observe in that experiment, let's say from substrate inhibition, like we sketched out, where the rate goes up and then comes down with concentration of S, then what mechanisms can we write down that have that sort of behavior? And what other mechanisms can we write down that don't have that sort of behavior? And so the ability to be able to take what we're thinking about and to work both forwards and backwards is a valuable thing.